This one for all my peeps that pass. God bless they rest. And check it out. Now I'm pound cause it's mad real.
Yo, it's time for Carnegie Mellon University's Future Data Systems Seminar Series. This seminar is made possible by Google.
Let's get started. We're super excited today to have Will Manning. He's the CEO and co-founder of SpiralDB. They are the main company building out the new Vortex file format, which has recently been turned over to been anointed as a Linux Computing Foundation project. So as always, if you have questions for Will while he's giving the talk, please unmute yourself and feel free to ask at any time. So that way it's a conversation for Will and not him talking to himself in Zoom. In the office in New York City, although there's other people around you, so like, you know, you're not like in your basement by yourself. You'll be okay. And so again, Will, thank you so much for being here. The floor is yours. Go for it.
Cool. Thanks for having me, Andy. I guess I'll start out, just a quick agenda, going to cover some introduction and background, just more like on the ecosystem and where Vortex fits in, core concepts. A lot of this talk, it's like I'm trying to nail in the extensibility of Vortex. So I should actually go back to the title. I originally called this LLVM for file formats, and then I was told that MLIR is the cool thing these days. And so I had to correct it. But then talk about the default components, stuff like encodings. We'll go through the file format byte by byte. And then we'll talk about some of the more interesting and novel stuff around how we do sort of compute pipelining, and finally like some benchmarks and some concluding thoughts. Leave some time for Q&A at the end. So about me, I studied operations research, math, and CS 15 years ago. Did reinforcement learning way before it was cool. I was a derivatives quant, and then I was at Palantir for about 10 years. I think I was arguably, or probably not even that arguably, the senior most engineer at the company when I left. I sort of one of the key folks behind Foundry, which is their exabyte scale data platform. That's like their main product these days. I was, at some point, I think I ran every single team at the company that read or wrote bytes in any form. And then now I'm CEO and co-founder of Spiral, which actually just means that I'm the worst systems programmer at the company. So macro hardware trends, because I think sort of, started the bare metal. A lot of the software constraints actually just, and the changes in data systems over time really come from shifts in the underlying hardware. So, early 2010s, it was large pools of this like homogeneous compute. It's like all CPUs are pretty fungible, lots of RAM. Mesos was just pretend everything's essentially a giant single machine. And there was a lot of work around like, okay, we have this hierarchy of sort of RAM is faster than disk, which is faster than the network. And that was like a totally immutable state of the world. Now compute's heterogeneous, it's probably never going back. Either the AI boom will continue and GPUs will continue to have more money behind them, or it will explode, and then GPUs will be abundant but cheap, in which case I expect data systems will incorporate them in other ways. I think the speed hierarchy that I outlined still holds for latency, but what's interesting now is there's been a flippening in bandwidth. So, network cards on a P5 in AWS, you can get about 8 times the bandwidth through the network cards that you can over the PCIe bus to a GPU. And, you're seeing the storage bifurcation towards object storage, which is cheap, but high latency, effectively infinite throughput, and NVMe when you care about things being fast. And then, a model I have, this is my model of sort of the evolution of data systems over the last couple of decades. And all models are wrong, some are useful. But I think, you sort of had 30 years ago, 30, a little more, Postgres was released. The core thing there was it was an application database, and the scale limits on the system were sort of like it was determined by a human typing something into a keyboard somewhere, or at least clicking a mouse. And then sort of the big data era was when we automated data collection, and there was sort of this like monumental shift. I mean, there was a Cambrian explosion. There was a big shift towards columnar analytics databases, all the web scale, Mongo, ClickHouse, everything else. And then I think that sort of has culminated in the Lakehouse, which, I think as Andy and Michael Stonebreaker pointed out in their papers, all this came around. It's just basically like, oh yeah, sweet, we invented tables, guys. Been around forever. And then I think what's different now, seeing this sort of emergence with the heterogeneous hardware, like we now have machine scale outputs. So, big data was machine scale inputs, but human scale outputs. I'll distill terabytes into a dashboard. But now I might need to stream terabytes per second to a GPU. And that just looks quite different from sort of classical databases. Like you would never do that via JDBC. The other thing is composability. So obviously Apache Arrow has been wildly successful for in-memory sharing and sort of inter-process communication. I think Ian from Columnar is talking about it. But the Arrow file format is basically uncompressed. It's just Arrow IPC in a file. So it's not actually ideal for long-term storage. On the flip side, on the long-term storage side, there's sort of Iceberg and Parquet. Iceberg wraps up. Iceberg is a table format. It's useful for essentially versioning analytic transactions, transactional updates, and for actually mainly consolidating metadata. And I would actually argue that the primary reason Iceberg is valuable is that it was a lot easier to add a new standard and wrap up Parquet than it was to actually evolve Parquet. But Parquet is what defines sort of how the bytes are actually stored. And you can sort of see this, Parquet predates the other two standards by at least a few years. So is Parquet good enough? It's widely supported. It's mature. It's columnar. It's kind of reasonable performance. Taking Hannes's quote, the format is great compared to CSV. But again, Betteridge's law of headlines, you kind of know that my response to is Parquet good enough is going to be no. It's borderline impossible to evolve. There are dozens of implementations outside of the Parquet project. I think the Wikipedia page lists almost 20. The recent addition of the variant type happened. I can say that it happened, but it was, I think, slow and very painful for all involved. And then there are just a lot of deficiencies in terms of the metadata. It's not, those are evolving over time, but they're not designed for object storage. It's ON in the number of columns that you have rather than ON in the number of columns you read. So for very wide tables, it's quite a lot of overhead. And then the biggest problem is that the compression is slow. So you get good compression ratio, but it really leans on, especially these days, Z standard to get a good ratio. And Z standard has pretty limited throughput. So what is Spiral? I'm just telling you this for 1 second so you know why I care about this problem. Like I said, and you probably guessed, I put myself in that third bucket of databases. So we care a lot about stuff like data loading, multimodal data into a GPU. I usually say complex data at machine scale. It's really, I think data lakes are stupid. Like most people shouldn't use them. Why have files are a poor user interface? It's better to have a database management system instead of every end user sort of building their own. So the reason that people don't put video in databases is actually arguably a product efficiency rather than because they don't want to or shouldn't. The funny thing about Spiral is it's optimized for throughput. So like I said, sort of my party trick is stuff like I want to stream this straight to a GPU. We also do columnar analytics, but the pre-training is sort of probably the main use case. So key quotes, I think I mentioned this was earlier on the slide, but sharing files in S3 is sort of an infinite bandwidth way to share between systems. And that's effectively the real key insight behind Iceberg. So you can transit systems between, say, Snowflake and Databricks. But like for GPU data loading, as I mentioned, the network card has about 8 times the bandwidth of the PCIe bus. So the only practical way is actually to stream bytes straight from object storage, and Parquet defines how the bytes are stored. So I care a lot about how the bytes are stored, which is why we made Vortex. The idea was that sort of existing open source file formats were not going to cut it. I mean, Parquet is the one that I beat up on the most because it's the most common, but it's honestly the best of the breed. And we wanted to build one. And so a lot of this came from, there's been huge amounts of progress in the research community. Actually, I think authors of a good chunk of these papers are on this call, either from, I annotated the ones from the FFF group at CMU, but also obviously sort of Peter's group over at CWI has a few, TUM has a chunk, and there are a bunch of papers that I didn't even include on this list. But the other thing is that industry was also far ahead of Parquet, and tier 1 tech orgs basically just keep building Parquet replacements that are specialized to their use cases because it turns out there's too much upside in specialization to ignore it. So there's Capacitor, Artis, Nimble, which is open source, but pretty much only used at Meta, Amidai, which came out of Microsoft recently. And then The other thing you could see is DuckDB has its own native format. ClickHouse has its own format. It turns out that storing these things in a sort of specialized way, as I said, has like huge performance upsides. So as we were designing Vortex, we thought, could we obviate the need for all of these custom file formats? Like, can we make an open source alternative that is kind of, I think, the equivalent of what Data Fusion is for specialized systems or what DuckDB is for, say, like join algorithms research? It's like, can you build the industrial sort of base? And then if you actually want to make progress, like how do you make it a harness for that progress? How do you make it extensible enough? How can even these industry closed source implementations hopefully not start from scratch? They said it's open source forever, as Andy called out at the beginning. We started it early last year, and then we donated it to the Linux Foundation earlier this year. So it's an incubation stage project at LFAI and Data, which is the same sort of here as Delta Lake, and which at least made me happy. Here's a fun quote from Wes. It's like, as I say, the goal here is to put sort of the cutting edge research with an industrial strength sort of implementation. So the project goals, we wanted it to be extensible and super future proof. That's actually the most important thing, because I think you can see goal number one is how do we stay at the cutting edge, and then goal number two is how do we get to the cutting edge. But I think file formats last for a really long time, and you see this with Parquet being, again, it's 12 years old. If we're going to replace it once, it needs to last for at least another decade, preferably longer. And in general, future proofing, I guess we also mean preparing for stuff like GPU compute. And so that's sort of in multiple senses. Like, here are the hardware shifts that we already know are underway, and then preparing for, avoiding the calcification, basically. The other thing we wanted was just performance. So we benchmark every commit and every pull request against sort of the best available Parquet implementations. Turns out DuckDB writes the fastest Parquet files, though they write very weird Parquet files. But yeah, our goal was, and I think we'll get to the perf later, at least 100 times faster random access. We want faster scans, faster writes. The lowest priority was sets. Like, we want size to not be a deal breaker, but at least by default, as long as it's kind of in the same ballpark. I don't think anyone's complaining that Parquet files are massively too large. And then the last thing is,
Can you share what you mean? Can you share what you mean by like the DuckDB writes the weird Parquet files? Because it's kind of goes like the balkanization of these implementations, which I guess Vortex wants to avoid.
They consolidate all of it's sort of stuff allowed by the spec, but they consolidate all of the row group metadata so that you can get it in one read instead of writing the row group metadata alongside each row group, which I don't think I've seen in any other implementation. And they also size it so that every column chunk only has one page. So the row groups are sort of sized to get, because they wanted to consolidate that metadata further. So it's how do you align so that essentially the column chunk metadata applies to single pages. So it was certainly allowed. It was just a much more extreme interpretation of the spec than I think most people, any other implementation uses. And it's very fast, to be fair. Like, those are good optimizations. Yeah, and then the last thing is we want it to be interactive, and I think we lean hard on Arrow. So I sometimes try to describe Vortex as the first sort of truly Arrow native industrial strength open source columnar file format. So we lean on and use Arrow quite heavily throughout the project. Sort of design goals as we're doing this, we wanted to move decisions from the spec writer to the file writer. So that's another way of avoiding calcification. We'll get to this later with layouts, but Vortex files are actually largely self-describing, and the file format itself is extremely minimal. And so that lets us do stuff like, should we have row groups, is a decision that we can actually defer, and it can be an area of open research. Like, should the default writer have row groups or not? The second thing was just fixing the sort of known list of deficiencies in the metadata in Parquet. It's like, write a flat buffer, optimize the layout of all the metadata for object storage to avoid lots of high latency reads. Flat buffer is nice because the sort of deserialization cost is closer to, order number of reference columns. And then the last thing was, we wanted to design, just again, getting to this future proofing for supporting GPU SIMD, CPU SIMD, and fast random access. So fast random access read being I have an external index. I know that I need to look up row number 42. How can I do that as fast as possible? And that meant all of those things actually have overlapping constraints. It basically means encoding should be lightweight, avoiding data dependencies, and we have to cascade those encodings to sort of get a good compression ratio. All right, core concepts of Vortex. All right, first off, it has logical types. So arrow is great. Arrow has physical types. The type tells you exactly the byte layout in memory. And so for cascading compression, that's actually really annoying because it means you would have to enumerate every possible permutation of these arrays, and different arrays in the same stream, sort of the same, like a chunked one, would have different data types. So we had to implement logical types. It's not that exciting. 32-bit integers, UTF-8. More interesting is we have arrays, which corresponds to arrow, but support cascaded lightweight compression. And a way to think about arrays is it's actually a way to defer computation. It's like I have this array that is logically, say, fast lanes bit packed, but I'm just holding the compressed bytes underneath, and I can do operations on that and sort of stack those up. Compute pushdown, related to what I just said, we have a bunch of compute functions. Funnily enough, compute is sort of merging with the notion of arrays. You can think of it in coding as it's a transformation on compressed bytes. And so what we actually build up with arrays is sort of a logical query plan. Talk about that more later. And then layouts, which is pretty novel. So layouts are conceptually analogous to arrays, but the data buffers are lazy. And so they can live out of memory. And the row count can be larger than memory, so U64 instead of usize, and it lets Vortex be self-describing. So we write a layout into every file, and that lets us see sort of how the bytes of the file relate to each other. But it actually provides quite a general abstraction. You could, in theory, fetch these bytes from sort of non-file sources. So you could have a layout that fetches bytes from Redis if you really want, or like some caching layer in sort of the Vortex library. We've actually played around with using Vortex for columnar data in Postgres. So it's like you want to back this with sort of 8K pages. It's a little extra crazy. As I said, arrays are a way to defer computation. Layouts let you defer I/O. And so you can think of, in some sense, these are actually just both terms for essentially stacking up query plans in the query engine analog, but for a file format. The nice thing about deferring I/O is we can figure out how to evaluate and prune what actually needs to be executed. And so this is sort of the basis of how we build filter selection and expression pushdown. I've said this enough times. It's like layouts make the file self-describing. So it's like we can decide you want to write all of column A before you write any other columns. You can interleave them. You can have row groups, whatever that may be. And they're composable. There are also layouts for things like a shared dictionary. So if I have a bunch of chunks or pages that sort of share the same logical dictionary, I can do that. We have a layout for zone maps. We're adding one for Bloom filters. It's easy to sort of add new layouts over time for especially different indexing structures, or we're adding one for sort of chunkier data types. So like a German strings, you can actually prune sort of sub buffers, for example, from the layout. The other thing is every single one of those four that I just described is an extension point. So that you can add new compute function kernels, you can add array encodings, you can add new logical types, extension types, new layouts. The library has pretty good support for that. And the file format has sort of a hooks for all those things. So again, not to beat a dead horse, but we've taken a fairly extreme approach to extensibility. It's actually quite inspired. Even the title of this talk is inspired by Apache Data Fusion, which I know Andrew likes to call it LLVM for query engines. It's like I think we try to think of Vortex as sort of the file format or like storage oriented complement to Data Fusion in a lot of ways. Okay, that was a lot. I'm going to jump to the defaults. So this is, we ship with a bunch of encodings out of the box. We ship with a default compressor. We ship with default layout and layout strategies. And that's how we get quite good performance, batteries included. As I said, we have cascaded lightweight encodings, the sort of big workhorses, like we use, especially almost all of them are either classics, stuff like dictionary, which has been around forever, or latest stuff from CWI and TUM. So fast lanes in all of its incarnations, like fast lanes bit packing, RLE, and Delta, ALP, FSST, says them all here. We actually had a contribution, I'll get to this later. We actually have a p-codec array and we have a z-standard array, which is kind of fun. It violates my earlier point about lightweight compression, but we can support them. But the default compressor doesn't use those. And in general, we're going for like data dependencies are the enemy. And I'll hit this a bit later, but it turns out that if you want to support kind of the constraints for GPU SIMT end up being the tightest. And if you can design the thing to have good support for GPU SIMT, it tends to support CPU SIMD very well. And again, lack of data dependencies lets us do efficient sort of random access instead of decompressing a whole block. But again, avoid snappy and z-standard. We avoid traditional delta and run length, and we prefer dictionary and all the fast lanes flavored ones, ALP and FSST. This is just a plug for the fast lanes paper, which is great. We also have an open source Rust implementation. I know CWI has a C++ one. ALP. ALP is actually great. It's really intuitive. Turns out that decimals should just be converted to integers, and then you can use integer compression. This is a quick index of, I took all of the arrays and dumped their decompression throughput on my MacBook Pro. So dictionary of string is a categorical dictionary. So turns out that copying long-ish strings gets you lots of throughput. But I think bit packages from fast lanes, we got about 53 gigabytes per second on my laptop. You can see in general, they're quite a bit faster than say Z-standard, which is 1 to 2 gigabytes per second. So dramatically slower than say fast lanes. Then what we did is actually, in addition to all these encodings, we have what we call a compressor. Compressor is, you can think of as like an encoding selection strategy. Ours was inspired by the sort of decision tree in Better Blocks. It's not exactly the same because we changed a bunch of the encodings out. So this is ours. We have our own, but it's heavily inspired by the Better Blocks one. We just updated it with sort of newer compression codecs. But as I said, the compressor is an extension point. So Martin Lunkarek, who's the p-codec author, decided to contribute an alternative compressor, which we call compax. And so this is going for absolute size minimization. It mostly uses p-codec for numerical values and z-standard for all the rest. You can see he ran on some chunk of the New York Taxi dataset. Actually, default Vortex is 433 megabytes, which is smaller than Z-standard compressed Parquet. But then compact Vortex is sort of even smaller. It shaves off another 100 megabytes. The default layout strategy in Vortex is loosely ClickHouse inspired, but we're still playing with this. So what we do is we construct pages, just array chunks that have a multiple of 81, 92 rows that exceeds a megabyte uncompressed. We compress those. And then we buffer a bunch of pages into what we call a stripe. And so we flush pages once the compressed size exceeds 2 megabytes. And so this actually works pretty well instead of row groups because it lets us get sort of enough locality and good enough compression chunks. But then for, say, strings, you might have many fewer values than you would for relatively low cardinality integers, which pack extremely well.
When you say you're experimenting with it, it's not so much experimenting with the layout because that's sort of fixed in the file format. You're experimenting with
the strategy. It's like, how do I choose the layout? What layout do I write into the file? So this is like completely open. Here's my plug for this. Is a great research topic if anyone wants to do research on top of Vortex. The thing is we can also encode basically Parquet. Nick, who's on the call, it's on his backlog of things he's dying to do when he has free time, which he does not because he has a 4-month-old in the startup. But is to write Vortex Parquet. So you can actually pretty trivially replicate Parquet with a chunked array or a chunked layout of struct layout of chunked layouts, where the sort of last, the first level chunk gives you row groups. The struct splits it into column chunks, and then the inner chunks as pages. And so, you can do that. Likewise, I think you can pretty trivially replicate Lance's file layout as a Vortex layout. Okay, so how do we do that? I'm going to go to, this is the file format in its sort of minimal form. There's a bunch of data pages and then a postscript. Postscript is a few hundred bytes. It has a hard limit of 64 kilobytes. And then there's an 8-byte end of file. And so start with the EOF. It's basically a version number, so we can increment it over time and say, like, this reader doesn't support the new version of the file. If we have to change something about the postscript, there's a postscript length. That's actually just a hint. It lets us make sure that we get the postscript in. If we didn't get it in the first read, we guarantee that we get it in the second read, because we will always get the end of file in the first read. It's 8 bytes. And in general, we size the first read such that we always get the postscript because we know that it's less than 64K. The postscript actually is quite amenable to both compression and encryption. All it stores is offsets and lengths. So it's essentially just byte ranges in the file. Get to know the top level topology of the file, and that's it. So it has what we call a D type. It's just the top level sort of schema that corresponds to the root layout. File statistics, which is really useful for sort of short circuit pruning. Like, if this is a partitioned something, can I skip this file entirely? And the footer. And then these postscript segments, as I say, it's just offset, length, alignment, and then details for compression and encryption. I guess I already sort of went through this. What's important to note is those can be written anywhere in the file. We write them by default towards the end, like both because it's easier to write the writer that way, and it's better for sort of I/O coalescing optimistic optimizations, but you don't have to. This is the full file. I'm going to zoom in on some sections. So I'm going to skim by this because there's a lot of information on this slide. So the footer has array specs, which is basically details about all the encodings used in the file, layout specs, details on all the layouts, segment specs, which are, again, this offset, length, and alignment, and then IDs for compression and encryption, which index into the compression spec and encryption spec arrays. And then you can see in the layout, we actually use segment IDs. And so the layout is basically pointing, it's dictionary encoding, what are the sort of actual byte ranges for all of these buffers within the file. And so in this example, I have a struct array, which is loosely just a table with 2 columns named A and B. One is a int32 and the other is UTF-8. And then the way that gets sort of reified by the default writer is that I have this struct layout, which will split it into columns. The columns actually it's at the top is this zone map layout. And our zone map layout is actually logically indexed. So it's every 8,000 rows. So it's, again, sort of click out, but you can change that. It's like easy to tune it if you want more granularity on the zone maps. And then, within that, we have these sort of physical byte buffers on the data pages that are chunked underneath. So I abbreviate flat for those are all these sort of like flat layouts with a segment ID. This getting back to the zone maps. What we store in zone maps is, you can think of it as per column statistics. So essentially the first row in that table will be the range of, say, 0 to 8192 exclusive rows. What is the minimum? What is the maximum for that data type? If it's nullable, what's the null count? Store sum. You can add other statistics over time. That's actually also a Vortex array. So it gets a little meta. But it means that we can compress those, which is nice. And then the data pages, as I say, it's sort of this ClickHouse inspired stripes layout by default. Writing a Vortex file, a user provides a stream of Vortex arrays, or you can just give arrow record batches, because we can actually convert essentially any arrow array can be 0 copy converted into the Vortex equivalent. And then we pass that to Vortex write options, which is where you plug in all the stuff around sort of the compressor, which is the encoding selection strategy, and the layout sort of selection strategy. And so we actually have some folks that are writing their own there. It's a relatively advanced use case, but if you really want to customize everything in the file and how it gets written, like we're talking, they have like some very large JSON payloads, and what they want to do is basically fully shred them and then Z standard compress the original in case they need to display sort of, the actual JSON in a UI. And so, they get to write their own sort of custom compressor and layout strategy for that. There's a very fun exercise for the reader. The answer is in our code base, but it's like we parallelize the writes without using row groups, which was kind of a very fun exercise. The hint is it involves vector clocks and is kind of akin to how you can insert rows and columns into an Excel spreadsheet. But it was a particularly satisfying bit of work by owners of TC on our team. Reading is totally different. So reading is, we actually, instead of having every query engine implement a file reader, we implement an absurdly optimized scan operator that we want to be used by every query engine. And so that means that it can be fast everywhere. It also means we're spending a lot of time optimizing the scalar compute. We don't do joins, but it means there are parts in the Vortex library that look or use a lot of techniques from a query engine. So a way to think about this in the limit is that the query engines that we're working with, I actually want them to push down everything that can be pushed through a join. It's like, how do I yield you sort of the sort of like the scan, so I send you as little data as possible and as like much sort of transformed as or close to the sort of target desired input for your join or aggregation as possible. And I call this moving the interface. It's actually inspired by Iran from Tiger Beetle. He gave a talk at Systems Distributed, and his whole thing is if you want to improve sort of by orders of magnitude, you have to change the interface.
So what would the calling query engine that invokes Vortex pass down? Is it like a expression tree? Does it look like the arrows expressions? Is it something Vortex
so
custom?
We have our own expressions. It's pretty easy to make an injection from sort of Data Fusion or any other ones. Like we have it for DuckDB too. They're pretty vanilla. It's actually that we have a subset of expressions that you would have in a sort of a full query engine. It's like I'm not going to support join. But yeah, it's essentially you just configure a scan with a relatively small number of sort of like builder options, and here's an expression to represent the query. So table scan runs over layouts and returns a stream of arrays. As I said, no requirement that's tied to a file. It orchestrates the bare minimum amount of I/O required for filter and projection expressions, and it runs the bare minimal amount of compute required for the filter expression. But then it runs zero compute for projection expressions. Like the thing here is you get this stream of arrays, each of which is lazily evaluated. And you can think of these arrays as essentially a tree, much like a logical plan that we might have optimized, but is wrapping compressed bytes. The most common function on these arrays is what we call canonicalizing. Canonicalizing is turning it into a form that's zero copy to arrow. And so in general, we'll push through we can push down a lot of operations. I'll talk about that in a second. But then in other query engines, so for example, in DuckDB, we can yield native vectors. We can give it a dictionary vector, but we can even give it like an ALP vector because it turns out that both we and DuckDB use ALP for floating point numbers. And so we can defer all of that decompression and just give it sort of the native form. And then ditto for sort of QDF. So as you start moving into GPUs, it's a different target. So we have lots of types of pushdown, as I alluded to. We have filter pushdown, just can think of as pruning rows based on maybe the zone maps, for example. Projection pushdown, pick column A, drop column B. Expression pushdown is sort of functions on columns. So it's like add 1, for example, to every value in this column. And then there's also selection pushdown. So that's sort of the same as expression pushdown, but if I have a mask. And so I might have masked out some rows. And then what's fun is behind these sort of operators, again, thinking of it like a compute engine's plan, we can actually implement different notions of compute. So you can have sort of kernels for GPU SIMD and also for CPU SIMD. The fastest way to do any work, the best form of optimization is to not do the work at all. So this is what I said earlier, especially for DuckDB, because we sort of both by default use the CWI phylogenetic tree of encodings. We can just pass them sort of encoded data. The next fastest is to produce n factorial handwritten fused kernels. No one's going to do that. But the middle ground, and this won't be a surprise to most of this audience, is to do things akin to sort of MonetDB and the classic sort of vectorization. Like, can we just hang out in the L1 cache as much as possible? So we're implementing sort of pipeline compute over 1024 elements at a time, reuse allocations. Like, the goal is to have essentially zero extraneous allocations from the initial read into the target buffer. So in the DuckDB case, if DuckDB gives us a vector, can we just not have any intermediate allocations at all? You just have some like reusable scratch space copied into the target vector. It rips along, does its work, grabs the next one. We then can hand fuse sort of the most important common kernels, so stuff like frame of reference with bit packing, dictionary FRLE. And then, because everyone who loves vectorization, there's also the people who love compilation. It's like, should you JIT it? For CPUs, we're not JITting it. But for GPUs, we JIT everything. And so this, in theory, kind of works the same way as the pipeline CPU compute. Construct these pipelines from the plan and iterate over 1024 element batches. But CUDA basically has its own. I think NVRTC is NVIDIA real-time compilation. It's actually pretty normal in CUDA land to just JIT all your code because there's so many different hardware architectures. Well, they're all NVIDIA, but 10 different versions, 12 different versions now. And then we also target web GPU. Turns out most of the same techniques apply. Some of the work we're doing right now, and this should land soon, is can we do the pruning and the orchestration from a file on the CPU? And then can we have the data buffers skip the CPU entirely? So just read them straight over the network, like through the NIC to the GPU device. And so then you can do decompression without having to pass the sort of data through the PCIe bus. Because as I said earlier, a lot of the sort of high-end GPU machines have an order of magnitude more bandwidth through the network cards than they do through the PCIe bus, which is sort of a fun fact. I've really abused this horse or hinted at too many times, but it turns out that GPU SIMD overlaps with CPU SIMD in terms of what makes it work well. I think in practice, GPU SIMD has the tightest constraints. So if you meet those constraints, it's trivial to basically make it work nicely on CPU SIMD, and random access reads are even more trivial. So here's some bits on Vortex from out in the wild, as I say. AnyBlocks, which won best research paper at LLVM last month. I would paraphrase AnyBlocks as the best way to make Parquet fast is to embed a WASM build of Vortex. It turns out that WASM SIMD is not far off native performance, and you get just dramatically faster performing Parquet, which this was kind of fun for me because we obviously used some of the TUM research, and then this just appeared. I had no idea they were doing it. Liquid Cache, it's work by Wisconsin-Madison. Shangpeng is great. We're actually sponsoring this year of his PhD alongside Influx and I think Battleplan because he's just great and does great work. This is integrated with Data Fusion. An earlier version of Liquid Cache, there was an issue that tickled me, which was it turns out even having an in-memory cache, it doesn't guarantee that you're faster than reading Vortex from S3 because we've optimized the living daylights out of it. We did a talk in April with Microsoft and Lance. So you plug Vortex into Spark. This was TPC. I think this was TPC-DS. Use less storage. This was just converting one-to-one Parquet files in an Iceberg data set to Vortex. And then for TPCH, we got a sort of full like 30% reduction in runtime. I think that would be more now. It's like 6 months later. And the product has gotten significantly faster since then, but pretty good speed up, even on Spark, which has tons of overhead. This one made me happy. So Mosaic, which is now part of Databricks, has this popular streaming data loader. So it's read a file from S3, load it into a GPU. It has its own custom file format, and Vortex was just 2x faster with no tuning. And then this one is, I had someone who recently moved from Lance, and we were 2.5 times smaller and about 10 times faster in terms of scan throughput. We also had a startup who I haven't asked permission to name, but I'll just tell the story. They came up to me and they have a Data Fusion backed API that was using Parquet, and they moved to Vortex, and it was a full 10x speed up in their P99 query time, which was pretty cool. turns out we're not the only new file format. So I took Andy's, nice screenshot of Andy's comment on Hacker News. There's sort of this whole phylogenetic tree, Cambrian explosion of file formats. So there's Nimble from Meta, CWI has fast lanes, we have Vortex, and then obviously the sort of recent FFF, F3. I think, there's a lot of overlap between this work. Like I will happily say Vortex uses almost all of the same encodings in the Fastlanes file format, and we looked heavily at Nimble when we were looking at some of the flat buffered metadata for the file is in the file layout stuff. And then F3, obviously, it's you guys use some of our encodings. Hopefully we'll pull a bunch of the F3 WASM stuff back into Vortex. I don't know. This is the nice thing about open research. Anyway, benchmarking. We run really extensive benchmarking on every commit and on demand on every pull request on dedicated instances in AWS. And so, this is if anyone wants to have a smackdown about their file format, I'm ready. So for random access, actually, we benchmark against both Parquet and Lance. We're the fastest by 137x compared to Parquet. This is the standard compressed Parquet sitting on NVMe, and it's grab 6 arbitrary rows spread out throughout the New York Taxi data set. Compression throughput, so write speed, where we write about 5 times faster. Take the geometric mean. It's the geometric mean of Parquet divided by Vortex. Again, so this is taxi data plus a good chunk of the public BI benchmark data sets. And then full scan decompression, which just give it to me as arrow. It's about 18 times faster than Parquet. For compression size, we're in the ballpark. So for some data sets, we're half the size. For some data sets, we're 50% bigger. The mean across the ones I benchmarked is the geometric mean is 1.16, so a bit bigger. ClickBench, we pretty much just destroy all the other file formats. DuckDB is the fastest. My personal favorite is that DuckDB Vortex is faster than DuckDB native when queried from DuckDB. And so, that's sort of a fun. I think we benefit from the fact that we don't have to make these files sort of updatable in place is the only guess I really have. And otherwise, there's a lot of similarity and overlap. You can see that for data fusion, we end up being quite a bit faster, something reduce the runtime by 30-40% here. And then Lance is 6 times slower. It's not even really in contention.
What's the difference between Vortex and Vortex Compact?
That's the one that uses pcodec and Z standard. So it's the alternate compressor strategy.
Yep.
That's it. For TPC-H, this is backed by S3. It's actually funny. Vortex Compact does a little better than vanilla Vortex. And I think it's because it's smaller and just downloading all the data from S3 is faster. You basically, it reduces to, I can just download all the data and then decompress it. But still faster than Parquet. This is again sort of TPC-H. This is on NVMe. Not quite as fast as DuckDB native now, but still competitive and much faster than the other formats. All of these have, by the way, I should have said that the X multiple is using ClickBench scoring. So geometric mean of query time ratio to fastest with a 10 millisecond shift. It's a weird metric, but a common one. And then I take total runtime because we look at both. So to recap, I think Vortex is state of the art, gives Pareto optimal performance. Like I said, for basically any metric you care about. I don't think there's another columnar file format that beats it at the moment. Then outperform specialized file formats. It's faster random access than Lance. It's faster for sort of GPU workloads than MDS. And then we'd have this sort of notion of extreme extensibility, which will probably make even more extreme if we add the F3 stuff. It's GPU native, industrial strength implementation. It's open source, contributions welcome. And this was the goal I said sort of earlier in the talk. It's can we obviate the need for all these custom file formats? Can we just sort of coalesce these things? Very, very excited to collaborate. As I said, I want it to be sort of what LLVM or MLA are for compilers, but data fusion is to specialized databases and what DuckDB is for OLAP research. So can we sort of make this a good harness for file format research? Because I think then we can, move those insights rapidly back into something that benefits the sort of actual practitioner community. It's already used in F3 and any blocks, hopefully in more places. Trying to, I'm very happy to sponsor grad students, especially on the IO stuff. We have integrations with lots of frameworks. We have bindings in Python, Java, C++. We have integrations with DuckDB, Data Fusion, Spark, boatload of Python frameworks. You don't have to build this. Build those with us. And then, if you want to do experiments, especially again for the researchers out there, more than happy to put our benchmarking infrastructure. You're welcome to use it to write your papers. Basically, I'm happy to bankroll that. So whether you're in industry or academia, we want you to build the future.
All right, I will applaud on behalf of everyone. Thank you, Will. The awesome talk. We have time for questions. If you want to go for it, just unmute yourself and fire away. If you can't speak, just post in the chat and I'll read for you.
I will. That was a great talk. I had a quick question about the scan operator, which makes a ton of sense. So there are two parts to the question. In the earlier part, you mentioned that in many ways, all the multimodal data that you see can be encompassed in a structured file format like this. How far did you think you want to take that? Do you want to replace file systems with that might be storing video objects and image objects with this, or would you go that far? And then I have a follow-up question.
I think it depends. So I think in at least most real-world use cases, even with files, you see a lot of, I'm going to say loosely relational operations on their metadata to say this is the video I want. And so, it might be filter to audio files that are more than 10 seconds and then actually push down a function that's give me the first 3 seconds. I don't know. So some of those might be externalized. Again, there's been a ton of work on video codecs, and it's not clear to me that we're going to immediately do better than the video codecs. But I think there's a lot of value in sort of making the metadata freely queryable so that you can do these sort of relational queries. And then for the video, you either externalize it or internalize it, depending on what the sort of data system being built needs. And so that's it can kind of go either way. I think there was a very cool paper though, called Frequency Store that we saw that was essentially doing a Fourier transform on images to decompose them. The intuition I got from it was it's roughly like a Taylor series where the more you can decompress it into columnar form, and the more columns that you choose to sort of mash together, the higher the resolution of the image. And I think there's a bunch of actually very cool work that could be done, especially for sort of GPU-oriented queries, where you see this already with folks doing image data, where they essentially create projections. Here's one where I decompose out this channel, or it has this sort of pyramid of resolutions, the ultra high resolution 15 gigabyte satellite version and all these downsampled versions. And it's I think we could potentially encapsulate that in the data system with something like Frequency Store and put those columns in Vortex and do something compelling.
Cool, that is great. And then the second part of the question is, as you're looking at feeding all this data in IO efficient fashion to the GPUs, you still have a ton of bandwidth left in the GPUs, or are we able to saturate that by having a whole bunch of scan operations going on to different files? How do you still keep the GPU that busy? There's a ton of bandwidth there, right?
The trick is, I think the best we can do is you have relatively high concurrency being orchestrated by the CPU that's opening a bunch of files at once. Again, S3, you get lots of bandwidth by having many connections. You get about 500 megabytes per second from a single connection. And the way you scale it up to get terabits per second is just having boatloads of connections. And so those could be against many files instead of just a single file. It then becomes it's a database problem. It's which ranges of which files do I need? And that planning, I think, happens on a CPU. And then it's you just pass the sort of encoded buffers to the GPU over the network.
Cool. Okay. Thank you. Awesome talk.
Thanks.
I thanks, Will, for the nice talk. I hope you can hear me well.
Yeah.
I had a small nit to just to not to confuse Andy's database of databases. You mentioned that MonadDB was the database system that was manipulating data in chunks of 1024. That is not correct. MonadDB is a column at a time system. So if your table would have 1 billion columns, it would actually use the granularity of 1 billion. It was vector-wise that
I'm
was
sorry.
using the notion of vectorized query execution. So not to create more noise.
Thank you for the correction. I will fix that before the
but
next time I use that
In
slide.
Will's defense, the title of the system is MonadDB/X100, right?
yeah, that's it's on us.
I was thinking of the paper more than the system, but fair to clarify.
But now a real question. You mentioned in the benchmarking section that DuckDB was either faster or slower in its own format on the ClickBench with Vortex. Was either faster or slower than Vortex in its own format. But there were kind of two experiments. The first one was the second one was on NVMe, and the first one on NVMe, Vortex was slightly slower than DuckDB's native format.
So,
but what was the first experiment referring to?
ClickBench, but we ran it against NVMe because official ClickBench runs against EBS, which has really weird latency properties. It looks like S3 the first time you request something, and it looks like slowish SSD the second time you request something. So we run ClickBench on NVMe, so you get sort of stable IO performance. So in
EBS. So that's in Amazon on. Okay.
Yeah, this is on Amazon. So we're running on a metal instance. So official ClickBench runs on EBS. In fact, prior generation EBS, it's really weird. Like GP2 EBS from like GP3.
Your explanation of that, because that has to do probably with the amount of fetches that you have to do, and basically with the way metadata is organized, or is because I imagine, yeah.
Yeah, my
why does Vortex profit more from EBS than from NVMe?
Yeah, I didn't. I think we profit more from NVMe. Was basically what it came down. Like we were faster on NVMe. I think on official ClickBench we're a smidge slower, but on the ClickBench we run on every commit, it's against NVMe. Like it's modified to run on NVMe, and Vortex ends up being a bit faster.
Thanks.
So I think we have more IOs.
What would be the reason for that?
We haven't tracked it all the way down, but I assume it's like there's some differences in IO. Like we tend to have longer sort of runs of a given form of compression. So, you know, our pages might have many more elements, whereas I think DuckDB compresses every 2048, if I recall correctly. So there's like somewhat of a different granularity of sort of the compressed buffers, and, you know, there's different IO planning. So I'm not sure that the short answer is we haven't debugged it or like profiled it quite far enough to know exactly what the difference is. But that's sort of the intuition, is I think we gain in some cases by, if you have a long run, you know, we might actually end up more compressed. Like if you bitpack integers, we might bitpack 256,000 integers into, you know, 2 bits each with F4. And so I can just rip through that pretty fast. The other difference is, I mean, to be fair, Vortex uses fast lanes bitpacking, and DuckDB, last time I checked, uses the Lemire.
Yeah, it doesn't use that. It uses slower bitpacking.
Yeah, it uses slower bitpacking. Yeah. So it could also just be the bitpacking, because we use so much bitpacking.
Right. Final question. Sorry to monopolize this. You kind of praise the approaches like AnyBlocks and F3 that propose to use WASM, but is WASM not kind of a complete blocker for running fast on a GPU?
Oh, it is. The value for WASM is actually, I think, purely in forward compatibility and shipping changes to the file format. So it's nice because it means that old readers can read the newly written file slowly instead of being able to read it not at all. Like you would never depend on a WASM thing, right? Like I don't think we would ever ship an encoding in WASM only form. We would ship an encoding where you say it's readable since, you know, some older versions that doesn't include that encoding. And so I say I will bundle a WASM thing of, you know, encoding X, new encoding X, and the API would be it will decompress into Arrow. Like it just decompresses that buffer straight into like Arrow IPC. And so it's a dumb function to take opaque like what to the old reader is an opaque buffer. It's like basically run this WASM function and get some arrow, and then you can manipulate it. So it's just a way to ship new encodings without breaking old clients.
Okay, thanks. We'll get back
Yeah.
to you on the sponsoring bit. Bye-bye.
Oh,
Thanks
yeah.
for that.
Wait.
Thanks, Peter. Other questions? I just point out too, the WASM is like, it's like kilobytes per column, right? It's not massive. And it's meant to be as a backup solution.
Yeah. I mean, AnyBlocks does it completely differently. AnyBlocks has like a 70 megabyte
They
full
have,
WASM build of Vortex. But
yes.
yeah.
Okay. I have a lot of questions. Have you done the performance comparison of Vortex running on the GPU versus like CUDA or Rapids, like their in-house written implementation of a Parquet reader?
We don't have all of the encodings yet, but at least on the we have reasonable implementations of all the fast lanes ones, which are just we ported essentially Peter and Azim's work because they had a fast lanes GPU and ALP, and we're working. There was a recent thesis from TU Delft and like some papers on a variant of FSST for GPU decoding that we're working on. So we don't have all of the encodings yet. And like that's the thing that we're filling in that matrix right now with a bunch of GPU kernels. I mean, again, the sort of core bread and butter, simpler ones, ignoring strings, we get hundreds of gigabytes per second, which is like quite a lot faster than Z standard on a GPU.
And then one of the challenges, of course, is like with the just-in-time compilation systems is debugging them, right? But I guess in your case, because you're only compiling like a small kernel, not the full query plan,
Right.
the
It's actually a lot
complexity.
easier to isolate.
Got it. Okay. And then the just-in-time compilation basically gives you compatibility with whatever version of NVIDIA you land on.
Yeah, because it's for all the NVIDIA GPUs, it's like, you can think about it of GPUs have many more sort of tiers of memory access and
Yep.
sort of complexity of compute. And so we might say like there's this version for, NVIDIA version 9 and up, which is like Blackwell, I think, which has like an extra tier of memory access effectively.
Got it. And then can you comment on like what sort of methods or strategies you guys have adopted or would like to adopt to ensure like the long-term compatibility of both the Vortex file format, but also the APIs as well? Because you mentioned that like some startup is or somebody has this JSON stuff and they're writing custom layouts. So that if that API breaks in the future, then they're kind of screwed as well, right?
So the file format, I think we have good backwards compatibility guarantees right now. So any file you've written will still be able to read. That's the only guarantee we have right now. Turns out for like APIs, we're kind of preserving the optionality to break APIs, but I think it's just like active engagement with the community of people. Like I don't think your average individual is going to write their own layout strategy for a production system. It's like a relatively low cardinality of these startups that are investing pretty deeply in their storage engines. And I think I know all of them. And so it's more just like help them migrate. I mean, like Data Fusion breaks APIs literally every release. And that's why they do major versions every release. And yeah, it has hundreds of projects using it. I think, it's more like the incremental rate of breakage is decreasing over time, but it's not going to be zero, I think, on the API stuff. File format, back-compat guarantees we have to maintain. But for now, we don't have sort of strict forward compat in any way. So it's like, that's the thing to add. And especially if you have like a custom layout or something, that's going to be a thing where you have to link in the code that parses that layout. No, there's not sort of a WASM. I mean, we could write a WASM equivalent for that at some point in the future. Like again, akin to F3, like all of these can WASM.
We thought about that. I think we passed on that. I forget why though.
It gets quite gnarly. I think the API surface area for layouts is like larger.
Yes. And then I don't know if you mentioned this or not, but like Vortex is written in Rust.
Yeah.
What are you guys doing to dissuade, again, randos from the internet writing their own Python Vortex reader or C++ Vortex reader, like to avoid that sort of balkanization that Parquet suffers from?
Mostly just get good bindings. Like we have good Python bindings, we have good Java bindings, we have good C++ bindings, we have data sources. Again, we benefit a lot from the arrow integrations. Like it turns out in Python, you can integrate with like several dozen different frameworks just by implementing the PyArrow dataset API. So we have Py, and then we have sort of special cased bindings for the engines that we care, like, want to invest more deeply in or partner more deeply with, but we have good catch-all ones that we sort of do via Arrow. And then, C++, it turns out that I think if you can get like Rust C++ sort of like nice interchange pretty easily. And so I think that's like the only compelling case for reimplementation, I think, is from C++ land, because any other reimplementation is almost surely going to be much slower. Like C++ is going to be the only performance competitive one. And so there, I think the strategy is just like have good C++ bindings. We even talked to like the Snowflake folks about integrating it into Snowflake, and they're a big C++ shop, and they were pretty happy with let's improve the bindings rather than we'll re-implement it.
Yep, got it. All right, my last question is, can you comment on how Vortex might work with the Meta's recently announced OpenZL, like data-aware compression framework that came out last week?
Ooh, I didn't look at it closely enough, but it seems like they construct a DAG based on the structure of the data. I mean, we could, right? You have an OpenZL compressor and a bunch of OpenZL arrays. I think the hardest thing would be we would probably need arrays to represent the sort of leaf or like all the different component compression steps that they support. And then you could just use it. Like it would just work. Like we could have an OpenZL compressor. Like we already have the Z standard array, so you can read Z standard encoded data. So I think we would do something kind of similar. And it should just work. It's new encodings, new compressor.